All right, how's it going, everybody? We are here I'm recording this on Saturday, February 20th. Today we're going to be talking about section 7.3, trigonometric identities. This is going to be a bit of a transition from the things that we've been doing here. Chapter 7 was already a bit of a transition in our kind of focus on inverse trig functions here, which are typically pretty uncomfortable for most people to start getting used to. Um, really, our overall goal with Chapter 7 is to be able to solve trigonometric equations. And so, really, what we're trying to do is put together two big pieces that we need to be able to do that. One of the major pieces is we need inverse trigonometric functions to be able to undo trig functions so that we can solve for the variables contained within them. The other thing that we need to be able to do is we need to be able to manipulate or trigonometric expressions to simplify them pretty typically, or at least to show that two trigonometric expressions are equivalent to one another. So what we're going to be focusing on for the next four sections, for the next 2 weeks, is a lot of trigonometric identities. And 7.3, 7.4, 7.5, and 7.6 are all going to deal with trigonometric identities, really coming up with statements that are showing that two trig expressions are equivalent to one another. So again, it's what we're kind of covering for the next 2 weeks here. That'll get us through 7.6. Then 7.7 and 7.8 are finally going to be solving trig equations, which in a sense is sort of like the goal of Chapter 7. It's just that most of Chapter 7 is covering the content that we need to learn so that we can do the solving equations. So it's sort of a minority of the content, but it's what we're sort of building towards with the first 6 sections of this chapter here. So what we want to kind of do first here is kind of make the distinction between an identity and an equation. Identities are a special case of equation. So sometimes it's hard to even tell that something that you're looking at should be considered an identity. The difference between an identity and an equation is that identities are true for every single value that the variable could possibly take on, whereas equations are only true for a specific subset of possible values that the equation could ever that the variable could ever take on. So I've given two algebraic examples here, and by the way, we're going to need to be pretty good at algebra here for these next coming sections. That'll be some of the stuff that we're going to be working on here. But what we can see here is I've given an algebraic example of an identity and an equation. This guy on the left here with these quadratics, this is an identity because this equation is true for literally every single value of x that you would ever plug in. There's no value of x you would ever plug in that would make the left side different than the right side here. These are two different expressions, x plus 1 squared and x squared plus 2x plus 1, but they will always evaluate to the exact same quantity for any value of x that you would ever plug in. On the other hand, this equation over here, 3x plus 1 equals 5, this equation happens to only be true for one single value of x. Almost every value of x that you would plug in here would make this not a true statement right here. If I plug in 10 for x, then we have 31 equals 5. Clearly not true, right? So most values of equations don't satisfy the equation. They have solutions, these small subset of numbers that make them true. Identities, every single value that the variable can take on is true, really just meaning this is just two alternate representations for the same quantity right here. So what do is, in general, we refer to our verb associated with these is that we solve equations. So here I could do some algebra maneuvers here, subtract 1 from both sides, divide both sides by 3, and end with x equals 4/3. I have solved the equation. I have found the solutions. On the other hand, identities don't really work that way because every number is a solution right here. So instead, we verify identities. If I want to, in a sense, you should think of the equations that we're going to see here today as propositions. I'm going to say, I think these two things are the same. What I would like us to be able to do is to verify that they are the same. And so we can do things like manipulating one of the sides to show that we'll get exactly the same thing as the other side here. So in this case right here, I might decide to manipulate the left-hand side to arrive at, let's see, if I FOIL this guy out, first is x times x, outer is x times 1, inner is 1 times x, and last is 1 times 1. And now I think that this is sufficient work for me to have shown, yeah, I have verified that those two quantities are equal to each other because I can see that that quantity right there is the 2x that I need to match up with the right-hand side. So kind of recognize that identities look like equations, but the verb that we use associated with them is a little bit different. Equations, we have an unknown value, and we typically have, in this case right here, there was only one solution to the equation. equations can have lots and lots of solutions, but the point is you don't become a special case of an equation, which is an identity, unless literally every single value of x or of theta or whatever our variable is will always make the equation true no matter what, right? So again, identities look like equations. It's an equal sign between two quantities, but identities are true for all values of the variable, whereas equations are only true for potentially no values of the variable, or one or a handful, or even a large number of solutions, but never everything being a solution for just a regular old equation out here. So the good thing to notice is that we've actually seen lots of identities this semester. Some of them are more like definitions, but these are things that are true for all values of the variable. So one thing that we started the class with is our trig function interrelationships right here. So we can say things like, we know that tangent is sine over cosine, right? This is true for every single value of theta that we can plug in here. We know that tangent has some limitations, right? That if cosine of theta were 0, then it seems like tangent is undefined. So it seems like at pi halves and 3 pi halves, or pi halves plus pi k. This is undefined, but for every value at which theta is defined, this is a true statement. It's not like we would solve this equation for theta, right? It's always going to be true. The other ones that we've seen here is we've seen that cotangent of theta can be defined either as 1 over tangent of theta, or it can be defined as cosine of theta over sine of theta. We've seen that secant of theta is 1 over cosine of theta, and we've seen that cosecant of theta is 1 over sine of theta. All of these are identities because all of these statements are true for every single value of theta that we're allowed to plug into these expressions, for every value in their domains. And again, all of these, because these all are defined as fractional values, all of these have some concerns about dividing by 0, but excluding those, true for every value of theta. The other identities that we've seen here, we've seen some Pythagorean identities. We're going to use these ones today. Sine squared of theta plus cosine squared of theta equals 1. That's one of our identities. We could take this entire equation and divide the whole thing by sine squared, and that would be giving me sine squared over sine squared would be 1. Cosine squared over sine squared would be cotangent squared of theta. And 1 divided by sine squared would be cosecant squared. Alternatively, we could have divided this entire equation by cosine squared. Sine squared over cosine squared would be giving us tangent squared of theta. Cosine squared over cosine squared would be giving me 1. And 1 over cosine squared would be giving me secant squared. Right? So here's our Pythagorean identities. These are true for every value of theta. It does not matter what angle is going into these expressions here. These general formats are always going to be true for all values of theta. Finally, some of the other important ones that we've seen out here are symmetry statements here. These deal with our positives and negatives inside of our trig functions here. Sine of negative theta, just picturing my tiny little unit circle down here. There's my positive theta, and there's my negative theta. And what we can see here on the unit circle is that these two quantities right here have the same vertical amounts up and down, but since one is up and one is down, we're going to get the negative of the sine value of positive theta, right? So here is an identity that's always true. Doesn't matter what the actual angle is. If you're looking at the sine of the negative of any angle, it's equal to the negative of the sine of the positive angle right here. Always going to be true. We had another one of these for cosine. Cosine of negative theta. Thinking about this exact same picture right here, what I can see is that if I go in the positive theta direction versus in the negative theta direction, both of these actually have the exact same horizontal amounts. And it's literally the exact same. Both of them went to the right by the exact same number of units. So it seems like the cosine of negative theta is always going to be the same as the cosine of positive theta right there. It's literally the same positive number, the same amount of x distance that both of these have traveled to get to their location on the unit circle right there. Finally, we can ask ourselves about tangent of negative theta. And this one, if you ever forget this one, just remember that this should just be sine of negative theta over cosine of negative theta. And therefore, this should be negative sine of positive theta over positive cosine of positive theta. And so it does seem like tangent of negative theta should be, it looks like negative, negative is right there, tangent. So it follows the same rule as sine does right there. Right? So there's a bunch more identities that we have already seen. These are symmetric identities right there, or identities associated with symmetries of our trig function. So all these ones, stuff we've already seen before. What our goal is going to be in the next couple sections here, I guess I should write this as in section 7.4 through 7.6, we'll come up with many more identities. We're in 7.3 right now. So we're going to see things like our sum and difference formulas. So that's going to be saying things like, if I have the sine of the sum of two angles, like an alpha plus a beta, what's that going to be equal to? Is there going to be some smarter way for me to write this expression so I don't have addition inside of my sine function right there? That's one of the things we're going to get in 7.4. We're going to get our half angle formulas that are going to ask things like, what's up if I take the sine of half of an angle right there? We're going to come up with exact formulas for these. So notice this is going to give us things like, we currently know how to do things like sine of 30 degrees. With our half angle formulas, we'll be able to come up with exact expressions for sine of 15 degrees, half of that angle. We're also going to get a double angle formula out here for things like sine of 2 theta. If you have twice of some given angle in there, is there some way for us to rewrite that in terms of just trig functions of just theta, like we kind of like to see that stuff? We're also going to get some product to sum formulas. We're going to get formulas that are going to help us rewrite the product of two trig functions of potentially different angles right there. And we're also going to flip that guy around and get a sum to product formula. And we're going to say if we're adding together or subtracting from one another two different trig functions of two different angles, is there a different way for us to write these? These two guys will be closely interrelated right here. So I think, if I'm remembering this correctly, this is going to be 7.4. I think that this is 7.5 and that this is 7.6, I think, if I'm remembering my sections correctly. And then in 7.7 and in 7.8 are where we're going to do solving trig equations. And that's because solving trig equations is going to require us to be able to perform these types of manipulations that we're going to come up with, and they're going to require us to have a good understanding of inverse trig functions. So 7.1 and 7.2 and then 7.3 through 7.6 are kind of concepts that are allowing us to perform the goal topic of solving trig equations at the end of the chapter out here. So to establish new identities, right? And that's what our goal is here. We have 5 new sets of identities that we're going to want to establish in the next 3 sections here. So to establish new identities, we need to be pretty dang solid with our algebraic manipulations here. So what we want to talk about right now is what are a bunch of algebra techniques that we need to be aware of and confident in so that we can handle the manipulations of our trig expressions here. So this is going to be kind of our most algebra heavy topics associated with this course right here. I definitely expect that most of us know most of these things. I don't expect that everybody has seen every single one of these algebra topics right here. It's absolutely the case that some of us are going to need to kind of pick up some new algebra techniques along the way with these. But these are going to be some things that are required associated with our identities and our equation solving with trigonometric equations here. So let's talk about what a lot of these algebra techniques are going to look like right here. All right. So some techniques we should expect to encounter. One of our most common techniques when we're looking at verifying trig identities or solving trig equations is to say, you know, the 2 trig functions that I am by far the most comfortable with are sine and cosine. So a lot of times when I see very unfortunate looking quantities like this, I say to myself, it'd be a lot cooler if this looked like sines and cosines instead of cotangents and cosecants, right? This is not my comfort zone right here. All right, so in this case right here, I think that I can go ahead and rewrite this expression right here. I know that cotangent of theta is the same as cosine over sine divided by, I know that cosecant is 1 divided by sine of theta. And it looks like now we need to remember what our algebra rule is that's associated with fractions within fractions. Our rule right here is, so I've heard this verbalized as keep, change, flip. I think of this as being a hinge right here with our larger of the 2 fractions. When we say keep, change, flip, that means we're going to keep the numerator exactly as it is. we're going to change from division to multiplication, and we are going to flip the denominator right here. So this is going to become sine of theta over 1. What you can now see, now that we've written this as a product of two fractions rather than a division of two fractions, is that I can see that my sine in the denominator is going to cancel with the sine in the numerator, and we're left just with cosine theta over 1. Divided by 1 doesn't even do anything. This just leaves me with exactly cosine of theta right here. So this is pretty interesting that this very unfortunate looking expression right here is actually just a different way for us to write cosine of theta, right? So the value in this is to say if we were ever to come across an expression that looks like this, I look at this and I say, oh no, but it turns out that this is exactly equal to like literally the simplest trig expression that I could ever possibly come up with, just sine of theta or just cosine of theta, right? So the point of these here is to say, rather than, if this were part of a equation that we're trying to solve out there in 7-7 or 7-8, I don't want to directly deal with this quantity. I want to be able to alter this quantity so that it looks as simple as possible for myself before I then go do something like solving an equation or graphing or something like that that we're trying to do out there, right? So this simplification, pretty important right here. And let me state in general our algebraic rule that goes with this. Whenever we have fractions within fractions, like a over b over c over d, we can keep the numerator the same, a over b, change the division sign to a multiplication sign, and flip the denominator. So this becomes d over c, right? So that's our algebra rule that we needed to know about here in order to greatly simplify this. And again, I hope you see the benefit. I would way rather work with the expression cosine of theta than the expression cotangent theta divided by cosecant of theta. So we want to be able to bridge the gap between the two right there. A little bit of algebra is required. So the next thing that we are going to do for ourselves here is help ourselves out by multiplying by a conjugate. And this is one of those ones that I know that I think that a lot of people have seen this. I think a lot of people have forgotten this, but have at least seen this in the past and often say to me, oh yeah, when they see me dealing with this guy here. Conjugate, I think, is a little bit less common. I think that people are a little bit less experienced with conjugate. And here's the thing that I'm thinking. When I see expressions like cosine over 1 plus sine, I like to think to myself, man, a 1 and a sine term being added together, boy, does that feel to me like some stuff that looks like my Pythagorean identity stuff. But here I always see that our Pythagorean identities always involve squared trig functions here. So one thing I can do to help myself simplify this is I can say, what could I do to end up with some squared terms with the sign right here? In a sense, I feel like it would be nice if I could square this sign right here. So what I'm going to do is I'm going to multiply this by the conjugate of 1 plus sine. This is going to be a fancy multiplication by 1. Remember that anytime you multiply anything by 1, you are not changing its value. So any version of 1 you ever want to multiply by, you're welcome to do that, and it's not altering the value of the expression. In this case, I'm going to multiply by a fraction where both the numerator and the denominator are going to be the conjugate of 1 plus sine of theta. The conjugate is where you have the exact same two terms, 1 and sine, but we're going to swap the positive for a negative, or if that was a negative, I would swap for the positive. All right? So let me maybe kind of define this over here. Right, so a conjugate just means for any sum or difference, it's just swap the sign that's in between the two. Conjugate of a plus b is a minus b. Conjugate of a minus b is a plus b right here. Notice that I have multiplied by a number that is just equal to 1, right? This is a fraction right here that the numerator is equal to the denominator. And the reason why this is a valuable thing for me to do, and I'm going to write some more algebra things right here. Oh, let me change my colors back again. I want to write some more general algebra stuff right here, is because if I do some like a plus b times a minus b, I'm going to go ahead and FOIL this guy out, and let's see the nice thing that happens right here. First is going to give me a squared. Outer is going to give me a times negative b, so that's a minus ab. Inner is going to give me a times b, but they're both positive. And last is going to give me b times negative b for a negative b squared. So notice when I multiply out a sum times its conjugate, or a difference times its conjugate, it's always going to be the case that those cross product terms cancel, leaving us with the exact same two terms that we started with, a and b, but both of them being squared. And it will always be that there is a minus between them because of the one minus that's always going to be part of this right here. So following that little bit of algebra in terms of a and b right here, I can see what I'm going to get. I can see that up top, I don't see anything special happening. It looks like we're just getting cosine of theta times 1 minus sine of theta up top. I don't see anything special there. But on the bottom down here, it seems like I'm getting a 1. So I'm following this stuff right here, right? I've got a plus b times a minus b. Looks like it should be giving me a squared. That's 1 squared. That's just 1 minus the second term squared. That was our sine of theta, right? 1 minus sine squared of theta there, right? Now I'm saying to myself, do I know any way to rewrite some of these terms right here? And I think I do know a way to rewrite 1 minus sine squared of theta. Using a previously known identity, I can see here that if I were to subtract sine squared of theta from both sides, 1 minus sine squared would just leave me with cosine squared of theta. So using a Pythagorean identity, I think I can rewrite our denominator down here as just cosine squared. And now it looks like I can cancel a cosine from top and bottom. Right? We might even want to go so far then. So I think that I'm good with this being a simplification. By the way, the reason I like this term better, or this expression better than our original expression, is because this I could rip up into two fractions if I want. Having sums and difference in a denominator doesn't really help me out that much because I can't pull this apart into a fraction with a 1 and a fraction with a sine where we started over here. But over here now, I could write this as 1 over cosine minus sine over cosine. So it looks like if I wanted to, I could go the one extra step right here and write this as secant of theta minus tangent of theta here. And the good thing is that I've now come up with a way to rewrite this that doesn't involve a fraction directly at all. I've just got this in terms of directly trig functions without ratios of, a division here, this cosine over 1 plus sine. Now it's true that secant is 1 over cosine and tangent is sine over cosine, but again, we'll get extra motivation as to what is going to be like our sort of our best possible answer here. With our identities, when we verify them, we're going to see in 1 second that we're going to write these in a little bit different way. Another thing that we're going to end up seeing is with our equations, we'll have like more kind of help, I should say, in understanding what's going to be the best simplified form here. But the point is we were able to come up with an alternate expression for cosine over 1 plus sine by multiplying by the conjugate of that denominator down there. That introduced some squared trig terms, and squared trig terms I was able to rewrite as its partner trig term, right? This guy right here happened, I'll indicate this one right here. This was our sine squared theta plus cosine squared theta equals 1, and therefore cosine squared theta equals 1 minus sine squared theta, right? So I used that identity to help myself rewrite this. And again, super not obvious to me that cosine of theta over 1 plus sine theta is the same as secant theta minus tangent theta. That's not obvious to me at all. I had to do a little bit of work to get there to verify that that was actually going to be the case, right? And it was dependent on my ability to do some algebraic techniques. This is sort of like quadratic type stuff right there, as well as using previously known trigonometric identities there. Right? So multiplying by a conjugate is a very common thing that we like to do in trig because multiplying by a conjugate ends up effectively squaring each term individually, and squared trig functions often lend themselves very nicely to rearrangement with Pythagorean identities. So this is saying if you ever see a 1 plus sine of theta or a 1 plus secant theta or anything that's like that where it's a sum of like a constant 1 and a trig term, we can effectively individually square those terms by multiplying by a conjugate without introducing any more stuff, because the conjugate will always cause those cross product terms to go away right there. So the conjugate's a pretty useful technique to have in your pocket right there for some of our potential simplifications out here. Another thing we need to be able to do algebraically is we need to be able to get a common denominator between two terms here. This is something that I know that all of us have seen many, many times algebraically here. A over B plus C over D. If I want to add these two guys together, then I would have to get a common denominator. In this case, if B and D don't have anything common between them, any common factors, then I would need a B times D. I would say A over D, or AD over BD plus CB over BD. And then I could rewrite this as one single fraction, AD plus CB over BD, right? We've all gotten common denominators and added fractions together before. That's a pretty common technique that we'll want to use if we have some unfortunate sums or differences right here of some trig quantities. So let's go ahead and do this guy here. Let's simplify this one by getting a common denominator. It looks like this has a factor of sine in the denominator. This has a factor of cosine in the denominator. So I'm going to want to multiply the first expression by cosine, top and bottom. I'm going to want to multiply the second expression by sine, top and bottom here. So let's go ahead and do that. So this should be equal to, switch back to my black. This should be equal to cosine of theta times 1 plus sine of theta divided by sine theta cosine. And I'm going to write these in the same order just so that we can see, just to make sure that we all see the multiplications happening here. So there's my first term. I've introduced the cosines. On the second one, I want to introduce some sine expressions right here. But the thing that I'm kind of noticing with this guy right here is maybe this is going to get some simplification. I'm noticing I got some cotangent stuff right there, right? So sine of theta times cotangent of theta minus cosine of theta, all divided by sine of theta cosine of theta. Now these have equal denominators, so it looks like I can add them together. So I think what I want to do to myself right here is I'm going to try and do myself a little bit of a favor, and I'm going to expand both of these things. I'm going to kind of blow some terms up right here, I guess. I'm thinking to myself, I want to distribute this cosine now. So I'm going to get cosine of theta. Cosine of theta times 1 is cosine theta. Cosine times sine. All right, so those are my terms from the first fraction here. I know that we have a common denominator, so I'm going to be able to write all these things underneath one common denominator right here. We got this common denominator of cosine times sine. Multiplication can happen either way, so these two denominators are equal to each other. And now I'm thinking I want to multiply this sine in through these terms right here. And here's the thing that I'm noticing. I'm going to do a little bit of side work right here. Sine of theta times cotangent of theta. That's really sine of theta times cotangent is cosine over sine. So that's actually just straight up cosine. When I multiply this sine times cosine here, I'm just getting cosine from this first product right here. I just showed that right there. So I'm going to get a plus a cosine of theta. And sine times negative cosine is going to give me a negative sine theta, cosine theta. And now I'm wondering what I'm getting from my little bit of simplification here. Well, look at the nice things that are happening. Here is a cosine times sine, and here is a cosine times sine, but here it's positive and here it's negative. It looks like those two guys just canceled. Similarly, it looks like I've got two copies of cosine right there, but those are both positive. So I'm just going to get 2 cosine of theta over cosine of theta, sine of theta. And now I can see, since I only have multiplication going on here, I can cancel cosine and cosine, and I am left just with 2 over sine theta, right? And again, I hope that you kind of see the value in this. This is not a good expression to have to work with. This is going to be an easy expression to have to work with. If I give you in section 7.7 this as an equation and say this is equal to 3, solve it, then you are probably going to struggle. But if we can go ahead and manipulate this until it looks like 2 over sine of theta, then it's going to be relatively easy for you to solve for the theta value that makes some equation true, right? So simplifying these trig expressions so that they become something that's simple for you to work with is very, very valuable to us here. And again, I'm going to keep on saying this. It absolutely is not obvious to me at all that this expression right here is going to simplify to anything nice and easy at all. I just can't see that. So what I've got to do is I've got to use all of my techniques here, right? Get common denominators, rewrite things in terms of sine and cosine, use the distributive property to multiply terms out, see things cancel, group some terms together, doing more fraction cancellation. All these algebra techniques are going to be really relevant for us to take really unfortunate looking difficult expressions and turning them into much, much simpler expressions right here. And in fact, I guess we could go so far, by the way, to call this like 2 cosecant theta. Like that's pretty minimized right there, right? So that might be another good final answer right here. I really like sines and cosines, so I wouldn't have any complaint if you stopped right there. But going one step further right there, calling that dividing by sine being cosecant could do. So one last algebra technique that we should talk about right here is simplifying by factoring. Here we want to see the reverse of the distributive property. Up here I drew these kind of like little like arcing shapes right here to indicate that I'm distributing by multiplication. I'm distributing a multiplication across a sum or distributing a multiplication across a difference. Factoring is the inverse of the distributive property, right? This is undoing distribution. So this is saying, do we see some place where we have terms that have some common things that we might be able to factor out? Well, I think there's one easy one to see and one hard one to see for this guy right here. I think the easy one to see is in the denominator. In the denominator down here, I have two terms, tangent theta, sine theta, and tangent theta. What I'm seeing here is that the first term has a factor of tangent, and the second term has a factor of tangent. Therefore, it seems reasonable for me to factor out a tangent from this guy. What do I have remaining from the first term? Remaining from the first term, what I didn't factor out is the sine term, right? And notice that just like distribution is a multiplication process, factoring is a division process. So it's like I divided tangent out of tangent times sine and was left just with sine. Here I'm dividing tangent out of tangent, and tangent over tangent should just be 1, right? So it looks like I have a sine theta minus 1 is how I could factor out tangent from the bottom. I have divided out a tangent from each of the two terms. Now up there in the numerator, what you should see is that we have a squared term minus 1, right? So I'm going to do my little bit of algebra work here in blue and say, this is like me having an expression that looks like x squared minus 1. And you know what this looks a lot to me like? Is this looks a lot to me like what we had with our conjugates up here. This is a squared term, x squared, and 1 is in fact also a squared term. It's 1 squared. It seems to me like I should be able to undo exactly this factoring that, or this multiplication that we did up there with conjugates. To undo the multiplication is to do the factoring. This is literally just going in the other direction. So it's sort of like we're starting at the bottom and we're working our way up. It seems like I could take my squared term minus a squared term, a squared minus b, and it seems like it should be able to be rewritten as the terms not squared, one with a sum between them and one with a difference between them. So it looks like this should be equal to x minus 1 times x plus 1. And all I'm doing is using the reverse version of that guy right there. So I think I need to draw a little line connecting these guys right here to show you that I'm just reusing this information right here. That's the exact same type of knowledge that we're using right there, just for sort of a forwards version and a backwards version of it, right? So what this is saying to me is it looks like following this algebraic identity, I can rewrite sine squared minus 1 as sine, let's see here, this should be sine of theta minus 1 times sine of theta plus 1. Now again, since everything is written expressed as multiplication, that's a term times a term divided by a term times a term. Here we had really subtraction happening in the numerator and denominator. In a sense, there's subtraction happening here, but this has been put into factored form. The essential thing that's happening is a term being multiplied by a term. So this now says to me that I can do some canceling that I was not able to do before. Again, here you can't just cancel one of these signs by one of these signs because we have other additions and subtractions that say that that's not a valid algebraic operation right there. Now that the entire expression has been written as a multiplication, I can go ahead and do my individual cancellations here. And it looks like I can rewrite this whole thing now as sine of theta plus 1 over tangent theta right here, which is a much, much simpler expression for us to have to deal with right there, right? That's much, much cleaner than the first thing that we were working with right there, right? So all of our goals with these is to say, let's take gross trig expressions and turn them into clean trig expressions by using lots of different algebra rules and the previous trig identities that we already knew, right? So we use these identities of like our Pythagorean identities came up. All the stuff that I've written over here in blue is all these concepts from algebra that we've previously learned, that we can apply to these expressions to help simplify all of them, right? So a thing to notice here is that it wasn't clear. I think that one of the things that you should still be left sort of wondering about here is saying like, how do I know when to stop? Like, how do I know that that's a good ending point for this guy right here? And the good news for us is that we're going to kind of get a little bit of help with that. I hate the phrase simplify, especially in classes like college algebra and trigonometry, because to me, I don't know what I'm trying to do with the expression, right? I keep on saying to you, I've already said it like 4 times in this video, our goal is to end up being able to solve trigonometric equations. The reason I'm telling you that is because when an expression says, or when an instruction says simplify, I'm saying to myself, simplify for what purpose? Why would I simplify this? If I don't know what I'm going to use that expression for, it's hard for me to know what a good simplified form would be for myself. I don't know if I want this to be 2 over sine theta or if I want this to be 2 cosecant theta. It's not clear to me which one of those is going to be better, and that's because we don't know what we're doing with these expressions yet. So see this as the sort of academic route that this is. We're trying to compartmentalize our learning. So right now what we're learning is just manipulation of expressions. But if you don't know what our end goal is, which we're not discussing until section 7.7 and 7.8, then it can be tough for you to determine for yourself. How do you know like when to stop? Why are we simplifying? It's a completely legitimate question to be asking right now. But what I want you to do is stay focused on knowing that the motivation for those is going to come in 7.7 and 7.8. So to that end, one of the really nice things that we're going to see here is that most of the problems that you're going to encounter are not going to be phrased like this because that's sort of arbitrary. What is the simplest form? If there's a billion different ways to write all these expressions, how are we supposed to judge what's the simplest form, right? So instead, most of these problems that you're going to end up seeing are going to be phrased as verify the identity rather than simplify the expression. This is really good. So I want to show you kind of where we ended up right here, right? We had this gross thing. And we got to this, and I was like, I guess I'm done right there. That was following the instructions, simplify the expression, right? Alternatively, we could take this. I wish I could get this all on the same screen. What I want you to see is that this on the left side and this on the right side, sine theta plus 1 over tangent, is exactly what I'm putting all together in one piece right here. So the way that you're slightly more typically going to see these be phrased is not simplify the left-hand side. It's going to say, here's something I'm telling you is straight up true. All I want you to do is verify that fact for me, right? So this is really, really helpful because this is showing you where your goal is. So this is sort of saying, pick one of the two sides, make that one side look like the other side. So this is not just an open-ended simplification question anymore. When it's phrased as verify the identity, it's now more of saying, here are two expressions, and you either need to work this side to make it look like this side, or take this side and make it look like this side. And if you can do either one of those things, then you've verified that this must be an identity, something that's true for all of the possible angles. So this is sort of our way of saying this is what your end goal is. It's giving you the answer in a sense. Your job is to fill in the gaps as to how do we get there. Now, that being said, we are going to add in one little restriction right here, and this is generally true of like all branches of math. Anytime you're ever trying to verify an identity in math, it's always considered most legitimate if you only ever modify one side of the equation. Right? So what I would never do here, for example, is multiply both sides by tangent of theta to clear the fraction on the right-hand side. That's not considered a legitimate move in verification of identities. When verifying an identity, if this is ever your instruction, you will never touch one of the sides of the equation. You just get to use it as knowing that that's your end goal. It's still really useful to you because it's still telling you what you want to end up with, but you are not allowed to touch it, so don't touch it. So one of your jobs is going to be to say, which side do I want to work with here? Which one is the one that I want to mess around with until I make it look like the other one? Pretty typically, 95% of the time, I'm always going to take the expression that looks more complicated and try to make it look like the one that's more simple. Almost always, that's my best move right there. Even if it turns out to not be the best move, I don't discover that until I've tried to screw around with the more complicated side and just can't get anywhere with it. So I always start with the more complicated side and only manipulate this more complicated side until it looks like this. And again, this is really, really, really useful to you because this is giving you a goal, right? This is saying, all right, whatever I'm doing, I got to make stuff look like that over there. So I'm thinking to myself, apparently we should only have a tangent remaining in the denominator. That indicates to me that maybe one of my algebraic maneuvers would be isolate a tangent in the denominator over here. How could I do that? Oh, look, it looks like there's a factor of tangent in both the first and second term of the denominator. I know I can factor that out, right? So I'm using the right-hand side not algebraically. I'm never going to touch it. But I am using it as my guide. It motivates my algebraic actions. It gives me like hints as to what I might do. It motivates my actions here, right? So don't ever touch both sides when you're verifying an identity. You would never do things like multiply both sides of the equation by 6, subtract 2 from both sides of the equation. You will never do that if the instruction is verify an identity. You only get to touch one side. You get to pick which side. I almost always pick the more complicated side. So let's just see how I would write my work here in this case instead. And again, I want to point out, this is the exact same problem as we just did right here. This was just phrased as simplify the expression. This one's phrased as verify the identity. It gives you the answer. This is the answer that we got up above right there. It's just saying, just get to the answer. I'm telling you that they're equal. You just show me how they're equal. What math could I do to verify that they're equal to each other? So here now I could write this as only manipulating the left-hand side here. Write this as the sine of theta minus 1, sine of theta plus 1 by factoring, quadratic factoring in the top, regular old factoring in the bottom here, factoring out that factor of tangent. I'm not manipulating this side. It's just going along for the ride. Now I can see I cancel, and I am left with sine of theta plus 1 in the numerator over tangent theta being equal to sine of theta plus 1 in the numerator over tangent theta. And now I give myself my satisfactory little check mark right there saying, I did it. I verified the identity right there, right? We're not coming up with solutions to an equation. We're showing that two distinct quantities that look different are in fact the same thing by manipulating one of them to look like the other. Cool. So there is our first identity verification. We're going to do so many of these in the next couple weeks right here. There's our very first one. So let's do a whole bunch of these now. Now today, I kind of at this point, I'm basically just going to rip out a whole bunch of examples right here because these are not all obvious, like where we're going with these. So there's a lot of sort of like, I don't want to say like subtle strategy, but like things we got to kind of like learn and get used to here. There are things that most people haven't done. And so this is usually new to you when you're taking this class right here, right? So let's go ahead and do a bunch of these guys here. So our first real verify the identity problem right here. Let's go ahead and do this one on the left. Cosecant theta times tangent theta equals secant theta. So again, what I kind of want to like help you guys do today is to like kind of see, I want to like speak my thoughts as much as I can right here so that you know what I'm thinking as I'm doing these problems. And I think that in a lot of these cases, a lot of them, you'll be thinking the same thing as me, and so that'll help you validate your own thoughts. And in some cases, I'm going to think things that are quite different from you, and you can start incorporating the thoughts that I have into your own thoughts right there. All right. So for this first one right here, I think that my first thought is the exact same as your first thought, which is, cosecant, tangent, and secant, those are not my three favorite trig functions. That's a good thought right there. This, I think, is an excellent place for us to stop and say to ourselves, all right, I'm not dealing with cosecants, tangents, and secants. I want to deal with sines and cosines. Let's let that be our motivating thought right here. It's our wrinkle your nose hard at this problem and let that be your motivation, right? So how do we rewrite each of these terms? Cosecant is 1 over sine of theta. Tangent is sine of theta over cosine of theta. And since I have decided to manipulate my more complicated side, I am not going to do anything to secant. Leaving it alone right there. Now I'm looking at this side on the left over here saying, it seems like I need to get to secant. And in my head, I am thinking to myself, I know that secant is 1 over cosine. I'm never going to write that on the right-hand side of the equal sign, but I am thinking to myself that 1 over cosine seems to be my goal. And it's kind of sitting right in front of us right here, right? Since we're multiplying two fractions, we can go ahead and do some canceling from top to bottom, and it does appear that we are left with 1 over cosine of theta equals secant theta. This is now a good final line, and I'm going to kind of point out my sentence down here at the bottom. In every case, when you're verifying an identity, the final line, the line where you get to say, I'm done and I don't need to write anything else, is a previously known identity. This is the definition of secant right here. I don't need you to like convince me any further that these two things are the same because we have arrived at a previously verified identity. And this isn't even like a verified identity. This is straight up a definition that we got at like day 1 or day 2 of the semester, right? So this is the line right here where I'm comfortable just plopping down my check mark and saying, I have verified it. This one, we use the strategy of rewrite everything in terms of sines and cosines, and then try and combine some like terms, see if there's any cancellation that happens. And we made one side look the exact same as the left-hand side. So again, if you want, you can write your final line if this makes you feel more satisfied as secant theta equals secant theta right there. But I'm certainly good with you ending right there because there's no confusion that these two things are equal to each other. It is a previously known concept that we have already and again, this one's even a definition. It's not even a previously known identity. Let's go ahead and look at the next one here. Sine squared of negative theta plus cosine squared of negative theta equals 1. In this case right here, I'm slightly bothered by the fact that there's some negatives inside of this thing right here. So I want to use my symmetry identities to help me rewrite these guys. One of the things that I want to remind us all about is our notation for squaring right here. When we write squared on the sine term right here, what we're really writing for ourselves is sine of negative theta squared plus cosine of negative theta squared equals 1. This is just our shorthand so that we don't have to do multiple sets of parentheses. That's really what we mean when we put the square where we typically do on the sine squared and the cosine squared like that, right? The important idea here, though, is to recognize that squaring is like our outside operation and that the sine and the cosine are the inside operations that would need to be evaluated first. Right? So what I can now do is I can use my even odd identities right here. And again, every time I forget these, I just draw my same diagram right here of my positive theta and my negative theta. And I recognize that the cosine quantities are exactly the same. So I'm just going to get here cosine of positive theta seems to be exactly the same thing as cosine of negative theta. The x values of these 2 points are literally the same number. For sine of negative theta, it looks like the y values of those 2 points are the same number, but one's positive and one's negative. So if I go sine negative theta direction, I'm going to get the negative version of what I would have gotten if I would have gone sine in the positive theta direction. So in this case here, this seems to me to be negative sine of positive theta squared equals 1. Now I think I can, in a sense, do the squaring here. It seems like this is just my same way that I typically write cosine squared of theta. Over here, I'm squaring a negative number. And what you know is that squaring, for example, negative 3, that gets you 9, just like squaring positive 3 gets you 9. What I'm really saying here is squaring sort of eats up negatives because negative times negative is going to be a positive. So this is, in fact, going to give me back the same thing as positive sine squared of theta. It ate up that negative right there. Now we have arrived at a standard form of a previously known identity. We've arrived at the exact structure of our Pythagorean identity, and therefore I have shown that these are exactly equal to each, that this is a good identity right here. It's because I was able to manipulate this into looking exactly like a previously known identity, right? So every one of your final lines where I put the check mark next to it either needs to be a straight up definition, like we have in this example right here, or it needs to be a previously known identity. So let me just kind of write these little sort of comments right here. So as soon as you get to either something that's just a straight up definition or a previously known identity, that's when you are done and that you have verified the identity, right? And again, over here, we left the one alone every single step of the way. We never touched that other side of the equation right there. All right? So now that we've kind of got our identity verification underway here, let's go ahead and try all these right here. So what I'm going to recommend that you should do right now is this. Is that you should pause the video right now, and every single time a new one comes up on screen, you should do it yourself and then see if you can see if yours agrees with mine right here. This is a really good place for you to get some practice and some sort of validation that the things that you're doing are right or wrong. These things are going to take some trial and error. You are absolutely going to make some right moves and some wrong moves with these guys right here. That's the way this goes. You need to build up a little bit of endurance with this right here. Nobody just gets all these right on their first try. These takes trial and error, and that's okay. Don't expect to always just get a correct answer every time you're doing something here. You need to try stuff. You need to just try some things out there. So go ahead and try those things right here. All right. So looking at this identity right here, I'm first just looking at this left-hand side and saying, wow, that's way grosser than the right-hand side. Therefore, it seems to me like I would like to attempt to manipulate the left-hand side of this equation and try to make it look like the right-hand side. I'm seeing a whole bunch of negative thetas over here. So it seems to me like I want to use my even-odd identities here, our symmetries. And we've said these a couple times now, but we're going to use them again. Cosine of negative theta, same as cosine of positive theta. So what I'm seeing right here is this. On this left-hand side, I don't like any of these negatives on the inside of theta, and the reason I really don't like them is because I don't see any negatives on the inside over here, so I sort of have to use these. I don't have any way around it, right? I need to sort of eat up those negatives inside of the sines and cosines, and if we pop one out like on the sine, great. If we don't pop one out like on the cosine, great, right? I'm using up these negatives on the inside. So kind of what we learned from the previous example right here was, we learned on the previous example that it seems like I could rewrite, and again, notice this whole left-hand side right here. It seems like this is exactly the numerator in the problem that we have down here. The numerator of our fraction is exact. Ooh, our numerator is not quite the same. This guy has a plus right here, and in ours we have a minus down here. But the point is, I don't think we touched that plus sign anyway, right? That never was impacted by any of the stuff that we did right there. So by following those exact same steps right there, I think that we can go ahead and say that we are going to get here. Well, it looks like we're going to get a negative sine of theta squared minus just a cosine of theta squared, right? That was using my even odd identities up top. Similarly, on the bottom down here, it seems like this is going to be a sine of negative theta is the same as negative sine of positive theta. And I know that cosine of negative theta, that's just the same as positive cosine of theta. So I'm going to basically just ditch that negative on the cosine term right there. I'm going to go ahead and leave my right-hand side alone. Don't you touch that other side. Now, what do we got? What's going on up here in the numerator up here? It looks like I square this. Squaring a negative gives it the positive version. So I'm going to get sine squared theta minus cosine squared theta over. And what's going on down here? It looks like there's negatives on both of these terms. I feel like maybe I want to like factor out that negative, right? To get at like a sine of theta plus cosine of theta. There was negatives on both. Now there's negatives on neither because I factored it out. Now what I'm seeing to myself here is I have squared terms up here. I have two squared terms, a difference of two squares. Difference of two squares, we've already done this one. Difference of two squares was right here. Difference of two squares, or even better right here, difference of two squares turned into individual terms with a plus between them, individual terms with a minus between them, right? So I'm going to write that one down here. All right, I'm just copying down from stuff we already did up above up there. So it seems to me like I can rewrite this difference of two squares, and this only works if there's subtraction between it. If this was a plus sign, then I wouldn't be able to use this idea. But if this was a plus sign, then sine squared theta plus cosine squared theta would be equal to 1. I'd at least have somewhere to go with this guy. But this difference of two squares says to me that I can rewrite this now as sine of theta plus cosine of theta times sine of theta minus cosine of theta. That's my difference of two squares factored form. All divided by negative sine of theta plus cosine of theta. This is equal to cosine of theta minus sine theta. And it looks like we're in pretty good shape to do some cancellation right here now. Now it seems like I am able to cancel because I have a fully factored fraction right here, where this is a term times a term divided by a term. I couldn't do any cancellation top to bottom in any of these terms over here because we have addition and subtraction in our fraction. I've undone that now. I've factored this guy. Now it seems like I can cancel and cancel. And what are we left with? I am left with the negative. So don't forget that negative right there. That negative's still here. Negative sine of theta minus cosine theta. And that's going to give me negative sine theta plus cosine theta when I multiply it back out. And that's exactly going to be the same thing as our desired expression on the right here. All right, whatever. Just flip the order of those right there. Positive cosine and a negative sine right there. It looks like we got it there, all right? So, not directly obvious. This required us to both understand our even and odd symmetries right there, and it required us to be able to do some quadratic factoring right here, a difference of two squares. Then we did a little bit of cancellation. Don't forget that this was like a sine of theta minus cosine of theta divided by negative 1. There was a negative 1 that we were dividing by right there. And if we dropped it, then we wouldn't have had both these things being equal to each other right there. So maybe I'll just kind of point that guy out right there, right? That negative survived right there, right? We wouldn't just lose that negative. Dividing by negative 1, it turns out, is the same thing as multiplying by negative 1. It's effectively just introducing a negative into our expression right there. Cool. So we have verified this guy right here, right? So again, not necessarily obvious at all that this is true, but we manipulated one side to get it down to being obviously exactly the same as the other side right there. Cool. Let's look at our next example here. And again, I'm going to encourage you to pause the video and do this on your own. Give this guy a shot. And this one, especially this one right here, this one has two really good different solutions that don't quite look the same as one another. And I want to show you why I would think either of these. There's two different kind of good thoughts that you might have at the very beginning of this problem, both of which will totally lead us to a good verification of this identity. So I am, in fact, going to do this one two different ways. So I'm just going to copy this whole thing right here. Put it right there. And we're going to do this one twice. And so that's extra good because I'm guessing if you pause this right now and do this on your own, one of the ways that I do it is going to probably be the thing that you do right there. I'm sure there's more than two ways, but there's two ways that are, I don't want to say obvious ever, so I'm going to say obvious in quotation marks right there. All right. So here we go. One of the things that I'm thinking is this. As soon as I see tangents, cotangent, tangent, I'm thinking to myself, man, I don't like those trig functions. I like sines and cosines, right? That's always a reasonable place for us to go with this. And I should say, like 95% of the time, that's a pretty good move in general, is to convert everything into sines and cosines. It's kind of our comfort zone. It kind of gives us some common ground to work with. It causes me to not have to like remember my identities associated with our weirder trig functions, stuff like that, right? So if I was going to go the sine cosine route, here's what this might look like. I'm going to get for my numerator now 1 plus sine theta over cosine theta, because that's tangent, divided by 1 plus cosine theta over sine theta, because that's cotangent. On the right, I've still just got tangent. So I'm thinking to myself, by the way, this, because I'm never allowed to manipulate the other side once I've picked a side to manipulate. I know that this is tangent on the right and I'm never going to change it from that, but I'm thinking to myself, since I'm converting this whole left side into sines and cosines, my sort of like goal quantity is for this to end up getting written as sine divided by cosine, because that's my sine cosine version of tangent. So that's like my goal in my head, knowing that I've got my goal value of tangent on the right here. So what am I going to do? Well, I'm pretty unhappy about this expression. We have sums of fractions in a fraction right here. That's not great. So what I'm going to do is I'm going to rewrite 1 as getting a common denominator to add some of these guys together, because I want to change my complex fraction into being a simple fraction. But I can only do that if I just have a fraction in the numerator and a fraction in the denominator. So I'm going to combine these two terms and combine these two terms so that I can do that. So I'm going to now write this as cosine theta over cosine theta. I chose that because I want the common denominator of cosine. Over here on the bottom, since I have a denominator of sine, I'm going to choose 1 to be sine over sine. Equal to tangent theta still. And now what I can do with this guy is I can now add these fractions together, the fraction in the top and the fraction in the bottom. Then I will be in the form of just fraction over fraction, and then I can do my keep change flip right there. All right, so it looks like I'm going to get cosine theta plus sine theta over cosine, all divided by, same thing really, right? Still equal to tangent here. And now I can do my little keep change flip guy right here. I'm going to remind us about this one because everybody always forgets this one, and this one kind of comes up all the time right here. Our A over B over C over D. I think of that as like a hinge where I'm flipping up the bottom to be part of the top right there. I'm swinging it up, and that dot is sort of becoming my multiplication. It should be A over B times D over C. That's the flipped version of the denominator right there. So what I'm going to get for my new fraction now is I'm going to keep the numerator. I'm going to keep change flip. I'm going to change division to multiplication. There it is. And I'm going to flip the denominator. I'm going to flip this denominator fraction down here. And notice that these are all like factors in one big fraction now that we're multiplying these together. Since those are exactly the same, numerator and denominator, it looks like I can cancel them. And it looks like we are here at sine of theta over cosine of theta equals tangent of theta. Boom, nailed it right there. That one's pretty good, right? So going all in terms of sines and cosines was not a terrible idea for this guy right here. It caused us to build up a pretty gross fraction. Some of these fractions right here weren't awesome. But again, I always think sine and cosine is my comfort zone. It's always a place I like to head to with this. Now, that's only one way that we could verify this. Let's see another way that we could have chosen to do this instead. And here's the thing I'm thinking. It's kind of weird for us to do this, let's get everything in terms of sine and cosine, when our other side didn't include any sines or cosines. That seems kind of like an odd choice in a sense to make. Now, I kind of verbalized this to you that I knew that my goal was to make a sine over cosine, because if I'm going to convert everything into sines and cosines and show that it's equal to tangent, tangent in terms of sine and cosine is sine divided by cosine. So I knew that was my goal. But again, say to yourself, it's a little weird if I'm trying to prove something's equal to tangent to get rid of all my tangents on the other side, right? That could be a thought that you think right here. So if you're in that camp of people that thinks that, maybe a different thing that you're thinking as well. If my goal is to get this whole dang thing rewritten so it's just tangent, then what I want to do is convert all my terms on the other side to be tangents. That's not a wild thing at all to think right here. So let's see if we can go this route instead of saying, Let's convert everything to tangent since my goal is to arrive at tangent. And again, this is the value of these being phrased as verify the identity rather than just simplify the expression, right? This is giving us a hint as to what our final result should look like when we simplify one of the two sides. So I'm letting this guide my modifications that I'm making here, saying since I want the left side to eventually just be tangent of theta, I should be turning everything that I can into tangents on the left-hand side. And so what this looks to me like is this. The numerator is already as tangent-y as it could be, right? The denominator, however, 1 plus cotangent, well, cotangent is just the reciprocal of tangent. So I think I can write this guy as 1 over tan theta for the cotangent term right there. Right? Now what I see is this guy right here on the denominator, he looks a whole lot to me like these things over here, and so I'm going to do the exact same maneuvers as we did before. I'm going to get a common denominator with this guy and then reduce down to a simple fraction rather than a complex fraction. So I'm going to keep my numerator up here as 1 plus tan theta, but down here in the denominator, I'm going to rewrite this 1 as tan theta over tan theta so that I can add it to 1 over tan theta. Now I can actually add these together, and once I do, I'll be able to make this a simple fraction instead of a complex fraction. So 1 plus tan theta over, it looks like I've got a tan theta plus 1 over tan theta equals tan theta. And you should notice one little funky part about this that makes this feel a little bit different. You should notice that every single time that we've talked about this complex fraction, it's truly been a fraction divided by a fraction. But here it's more like I have a number divided by a fraction right here. We're still going to do the same thing, but I just kind of want to point out how I would think about this very slightly differently here. In this case, to me, it seems like we've got A divided by B over C. So all I'm going to do is I'm going to think of this as A over 1 over B over C. Now I can go ahead and write this as A over 1 times C over B as my rewritten version right there. So this is just saying I kind of want this, once we get partially a gross fraction, fractions and fractions, I want to make everything a fraction within the fractions so that I can use my keep, change, flip rule or the hinge rule right there to write that way. So in doing that, it looks like I'm going to be getting a 1 plus tan theta over 1 times the flipped version of this, which is tan theta over tan theta plus 1. And what do you know? Again, those are going to cancel, leaving us with tangent theta over 1. And we're left with tan theta over 1 equals tan theta. I'm cool with that being the last line right there, because they're obviously equal to each other, right? So both these routes totally worked right here. And I think that you should agree with me that this sine and cosine route was in a sense a little bit grosser than the tangent route right here. But then again, I know that most of us, and myself included, I'm typically willing to do like a smidge more work to hang out in my comfort zone, which is always sines and cosines. So it's not always the case that sines and cosines are going to be your best friend, but it's very, very often the case. And so I totally get people's desire to step one, rewrite everything in terms of sine and cosine on one side of the identity right here. Very, very common starting step. But again, recognize that here we had this motivation to maybe not do that because we knew that our end goal was to get a tangent expression. So maybe that's what guides you to say, you know what, I actually want to rewrite everything in terms of tangent, not in terms of sine and cosine, since that's my goal is to get a tangent expression over here, right? So again, all these things I'm talking right now about are my strategization. I'm strategizing right here. I'm saying, how do I even know what I want to do? And I'm allowing the simple side of my identity to motivate the way that I manipulate the complicated side of my identity over here, right? So like, stop and say some of these things to yourself before you get started. Don't just go plowing into these things, rearranging stuff. Like, stop and say, like, what do I really want this to look like at the end? How do I think I might end up getting there? Which of these terms is going to be the most useful for me to end up with? Those are questions you should be asking yourself rather than just trying to just do some math, right? So what do we got? A couple more examples right here. I think I'm going to do what I got. 3 more examples that we'll hit right here. And man, I think that these are all going to be very useful for you to see. So let's go ahead and keep on cruising along right here. So our next one here, sine theta over 1 plus cosine theta plus 1 plus cosine theta over sine theta. So this is adding these two reciprocal fractions together and getting 2 cosecant theta. I very much feel like this is my more complicated side of the identity, so I think that's the one that I want to manipulate. I know that my goal is to get at 2 cosecant theta, or what we know to be as not 2 cosecant theta, but maybe 2 divided by sine of theta, right? Cosecant is 1 over sine. Times 2 would be 2 over sine right there. So I'm keeping that in my head, but I'm never going to write that because I'm never going to manipulate both sides of my equation. Just keep giving you the crazy eyes every time I bring that up. So here we go. What do we think we want to do right here? Well, I'm looking for some motivation. Why would I do any one thing rather than just blindly doing math right here? Well, the thing that I'm seeing is there is no addition or subtraction on the right, but there is addition subtraction on the left. So that sort of says to me, I think I want to do the addition so that I can get down to having a single term, just like we have on the right. If there's one term on the right, then I should combine these terms to make one term on the left. That's my motivation to kind of get started here. Since I can see that we're adding two fractions, I think that I want to get a common denominator with this guy right here. So to get a common denominator, it looks like this guy has a factor of 1 plus cosine. This has a factor of sine. So I need this guy on the left to have a factor of sine in the denominator. I need this guy on the right to have a factor of 1 plus cosine in the denominator. So let's see if we can force those to be introduced right here. For the term on the left, what I need is I need there to be a sine theta in the denominator. And the only way to do that is to multiply by a sine theta in the numerator right here, right? So I'll write it this way this time. And then we'll multiply those two signs together to get a sine squared in a second here. For this one on the right, what am I seeing? I am seeing this only has the factor of sine in the denominator, so it needs a factor of 1 plus cosine. So I'll multiply that in the denominator, but if I'm going to multiply by the denominator, I better multiply by the numerator so I don't change the overall value of the fraction. So I've now got a 1 plus cosine theta times 1 plus cosine theta up there in the numerator, right? That was the original one, and this is the one I introduced with my fraction right there. Right? So, was this helpful? Questionable. What do we got right here? Well, it looks like we got the common denominator. So I do know that I can go ahead and write out my common denominator here of sine of theta times 1 plus cosine theta. Now we got to decide what are all these remaining terms that we got up top here. Well, sine times sine should be giving me sine squared of theta. Now I've got to be able to multiply out this 1 plus cosine theta. So what am I going to get? I'm going to FOIL out my product of two binomials here. So FOIL says first is 1 times 1. That's 1. FOIL outer says 1 times cosine. That's cosine of theta. Inner says cosine times 1. That's also a cosine of theta. Last says cosine times cosine. That's cosine squared theta. Allegedly, this is equal to 2 cosecant theta. Still don't see it. So, what do I see that we have up here in the numerator? It looks like I'm hoping for a lot of things to kind of go away. And so again, let's stop and think about our motivation. Like, how in the world do you know what you're going to do for your next step? It doesn't seem like there's anything just smacking you in the face saying, obviously do this. I don't see that here. So I'm going to stop and I'm going to go and consult my right-hand side. This is my magic 8-ball over here. I'm going to say 2 cosecant theta. What should I do next? Please guide me on my mission here. I'm thinking to myself, this is really 2 divided by sine of theta. I have a division by sine of theta over here already. What I seem to be hoping for is to end up with a 2 up top. And apparently what I'm also hoping is that this 1 plus cosine theta cancels with a 1 plus cosine theta up top. Well, what I'm noticing is I have some terms like sine squared and cosine squared up here that don't seem to have any place in my right-hand side over here at all. Do you know some way that we can rewrite sine squareds and cosine squareds? I do. I'm remembering for myself over here that sine squared of theta plus cosine squared of theta is equal to just 1. That is just the nicest simplification that we're ever going to get, right? So I'm seeing here that sine squared of theta plus cosine squared theta, they're both positive, should be giving me a positive 1 is what I can use to replace them. So I'm going to replace sine squared plus cosine squared with just the number 1. 1 plus 1 plus cosine theta plus cosine theta. And just to help the organization here, I'll cap my 1 right there so you can tell where that came from. All divided by sine theta times 1 plus cosine theta. Allegedly is equal to 2 cosecant theta. So it looks like I can simplify up top a little bit here. I'm now seeing that there's a common factor of 2 up in the numerator. That is a great sign for me. So I'm going to factor it out. Oh my goodness. Oh my goodness. What do you know? We have generated factors of 1 plus cosine theta both on the top and the bottom, and are able to cancel them away, leaving us with 2 over sine theta equals 2 cosecant theta. And that gets the check mark right there because that is the definition of cosecant. It's 1 over sine right there. So we nailed it exactly right there, right? So again, I think the lesson to learn from this guy right here is we got to be able to get common denominators. We got to be able to do a little bit of quadratic math of foiling out some binomials right here. And we've got to stop and consult the side that we're not manipulating. It really, really wasn't obvious to me what to do with this big gross numerator over here until I stopped and said, well, what's my goal? This was me pausing and strategizing for a moment, saying, I know that I'm looking for a 2 over sine theta. I've already got the sine theta in the denominator, so I don't want a 1 plus cosine theta anymore. It needs to cancel. And I don't see any squared terms anywhere, so those apparently shouldn't be there. And that guided me to think to use my Pythagorean identity to combine some terms. I'm recognizing the 1 plus cosine theta had to go, so I factored out the 2 to create a 1 plus cosine theta on top to cancel it away, and we were able to verify that identity with that guy right there. All right, so what do we got? We got 2 left right here. Let's do 2 more, and we'll go ahead and call it a video for this guy here. So what am I looking at right here? Tangent theta plus cotangent theta over secant theta times cosecant theta. I am hoping that you are thinking the exact same things that I am thinking for this guy right here, which is that we have literally all 4 trig functions other than sine and cosine. Even if we don't convert like every problem that we ever get into sines and cosines, this is like our worst case scenario. It's all 4 trig functions other than sine and cosine. I am hoping that you are very much on board with the idea of let's go in terms of sines and cosines here and try and get this to all be equal to, man, 1, really? Okay, so tangent, that's sine theta over cosine theta. Cotangent, that's cosine theta over sine theta. Divided by secant, that's 1 over cosine theta. Cosecant, that's 1 over sine theta. I want to show that's equal to 1. So what I'm seeing here is we have a sum of 2 terms up top. That sort of says to me, need a common denominator if we're going to combine them. We have a product of 2 terms on bottom, which says to me, that really is already just a single fraction. I just need to write it that way, right? Multiply your numerators, multiply your denominators. So here's what I'm thinking. Up top over here, our first fraction in the numerator already has a factor of cosine. It needs a factor of sine. So I'm going to hit this guy with a sine over sine right here. That's going to give me sine squared over sine times cosine. Similarly, right here, this currently has a factor of sine. It's missing a factor of cosine. So I'm going to hit this fraction with a cosine over cosine. That's going to give me a cosine squared over sine times cosine. All divided by, down here, I just have a 1 over sine times cosine. Now I can add my fractions together and check out what's happening up top right here. I'm going to add sine squared plus cosine squared, and you are very familiar with what we're going to get from that guy right there. We just used that once. It looks like that's just 1 right there. And so it looks like I am reducing myself down to 1 over sine theta cosine theta over 1 over sine theta cosine theta. Honestly, if you ended right here, I am cool with that because this is a number divided by the same number. Of course we're going to get 1. I think it's appropriate for that check mark to happen right there because that's clearly like a divided by a, and we got 1, right? Now, if you want to kind of verify this one additional step, we could certainly keep the numerator, change division to multiplication, flip the denominator, and now hopefully it's pretty clear that we're just getting 1 right there for that guy as well, right? So with some of these, I think it's you might be less convinced than other people that it's acceptable to stop at some certain location here, but I kind of I believe right here that we did it, right? We got a number divided by the same number. Of course, that's going to be 1 right there. It's a gross looking number over the same number, but it is in fact what we define any fraction to be as 1, a number divided by itself. And we can show with one extra little step if we want right there. Cool, cool. And so again, this one, I'm hoping that by this point in the video, you guys all have the exact same instinct as I have right there, which is get that thing in terms of sine and cosine. What a gross grouping of fractions right there, right? So let's hit one last one right here. I like this one. This is a good little manipulation. This is actually, didn't we kind of like partway do this one up top? One of the reasons I like this one is because it really is not obvious at all that there's one side that's like better to manipulate than the other side right here. We keep on picking the more complicated side to turn into the simpler looking side. These are very equivalent to me. And the other thing that's really important to me with this one is it's really unclear to me what I should even be doing. Like I don't have any convert to sines or cosines. I don't see any identities that I can use. I don't have any fractions I need to add together. Any of that kind of stuff. But what I am seeing here is whenever I see 1 minus sine of theta or 1 plus sine of theta, I'm always thinking to myself, I'm like, man, it'd be super cool if one of those things was squared because then I could use my Pythagorean identity. So every time you ever, and again, I think that people have been like taught in their math classes to like just do math or something like that. I don't know what the heck this is all about. But the point here is use your wishful thinking here as your guide. My wishful thinking here says to myself, man, I feel like this problem would be a lot easier if there was like some squared trig terms in there. Then get out your algebra beating stick and make them be squared trig terms, right? We have a technique for doing this. Use your wishful thing to say, you know what? I think I can make that happen. I think I can manipulate this thing to get the terms that I feel like I kind of want in there. I'm going to scroll up and remind us of where we've seen that. Ooh, we did some writing today, dang, didn't we? Didn't we do some writing here today? Here we go. Here is where we actually kind of already saw this one, right? We sort of did this as a verification already, but remember what we did right here. We multiplied by the conjugate because multiplying any a plus b times a minus b will give us the individual squared versions. And that very often leads us to some nice Pythagorean identity statements that'll help us condense some stuff down into something simpler, like the number 1 very often. So just for the sake of doing something different here, I'm noticing that in this guy, I manipulated the one that had a 1 plus sign as the denominator. So how about for this one, we manipulate going the other direction. Let's start with the 1 minus sign version and go the other direction here. And I think I want to use a conjugate so that I can introduce some squared terms so that I can reduce those squared terms to being something a little simpler. Oh my goodness, here we are. All right. So in this one, I'm picking the left-hand side just because I want to do something different than what we already did up above up there, right? So I'm thinking to myself, let's do our 1 minus sine of theta over cosine theta. And I want to multiply by a fraction that's the conjugate of the difference right here. So that means I want to multiply by 1 plus sine of theta. But I can't just multiply by 1 plus sine theta. That would change the value of the fraction. I therefore also need to divide by 1 plus sine theta so that I'm not like changing this at all, right? The other thing that's kind of guiding me on this one is it's like I see the 1 plus sine theta sitting right there. It looks like it's a good call for us to introduce that. I can see it, right? Now, why are we doing this? That's because 1 minus sine theta times 1 plus sine theta is going to simplify to something really nice. This is our difference of two squares setup right here. We're remembering here that we said a minus b times a plus b equals a squared minus b squared. All right. So I've got exactly that kind of situation right here. A minus b times a plus b should be giving me the first term, 1 squared. That's just 1, minus the second term squared. Why did we do that? Well, because I've got a different way that I can rewrite 1 minus sine squared. Now I know sine squared theta. The whole reason we like squared trig terms is because we can use Pythagorean identities with them. Right? So it looks like I can rewrite this numerator here as cosine squared. And that's going to get me there, right? It looks like we're going to cancel one of them with that, with the power up there in a sense, because we had 2 cosines up top. I'm canceling one of them away, so we only have 1. And it looks like we are, in fact, left with exactly what we had on the right-hand side the whole time. All right. So anytime you see addition and subtraction of sines and cosines and there's no squared terms at all and you don't really know where to go, stop and think about conjugates. These I feel like are the most underutilized algebraic tools that I see out there. It's the thing that people always forget, and people come to me and they're like, "Man, I've tried everything," and what they really mean is, "I tried everything but this one thing," and it turns out to be the one thing, right? So just don't forget about these guys as being one of your good algebraic techniques to it's our way of effectively squaring some expression, right? If you start with a minus b, the way that you can make it a squared minus b squared is to multiply by a plus b. Often, though, it ends up being an expression of fractions, so you need to multiply both numerator and denominator by that conjugate expression of a plus b. Remember that conjugates go both ways. The conjugate of 1 plus sine theta is 1 minus sine theta, and the conjugate of 1 minus sine theta is 1 plus sine theta. So it goes both ways with those pluses and minuses, but conjugates work by this identity right here, and it's a way of saying if you wish that something was the same expression but squared, then hit it with the conjugate, and that's the way that we can sort of introduce squares into things here. So we've got our general guidelines for verifying identities here. Let's just talk through this and call it a video here. All identities are always to be verified by only modifying one side of the equation. Typically, it's the more complicated side. The other side of the equation just exists to show you your goal for the simplification. It should be it's your little magic 8 ball of you saying, what should I be doing right here? Use what it looks like to motivate the things that you do on the other side. Right? Rewrite your sums and differences of quotients as a single quotient by getting a common denominator. Right? This just says rewrite sums and difference of fractions as a single fraction. I shouldn't. That's a much simpler phrasing right there. I don't know why I have the word quotients in here. That's just making that confusing. Right? That says add and subtract fractions by getting common denominators. Very often, but not always, it is helpful for us to rewrite everything in terms of sine and cosine. It gives us sort of some common things to work with. It's very rare that you're going to do an excellent job of verifying an identity if you have 4 different trig functions in it. Get a common place to work with. Sines and cosines is often good because sine and cosine identities often relate to each other. Sine squared plus cosine squared equals 1. We're going to see in section 7.4, 7.5, 7.6, we're going to get a bunch more identities where sines and cosines are going to directly relate to one another. There's like no identities where we rewrite sine in terms of cotangent or something like that, right? So getting in terms of sine and cosine is one common place of measurement. Keep your goal in mind. Even though you're not allowed to touch the other side of that identity, seeing the format of that other side should help motivate the algebraic actions that you want to perform on the side that you are manipulating. So you're not allowed to touch it, but you're definitely allowed to look at it, and that should be a helpful thing for you. So, as my closing statement, I'm just going to say these can be hard. And so I really think that my final statement right here really should be persistent. Don't give up. You need to develop endurance. You need to try more than one thing. You should be viewing this as a little bit more of a guess and check type thing. Then nobody just knows what they're doing with these. I got the advantage of A, I've done about 1 billion of these in my life already, and B, I did all these before I did this video right here. Like, obviously they look good when I'm doing them. Lots of these things take lots and lots and lots and lots of tries. Okay, not lots and lots and lots and lots, but like, it's not unusual for you to try 5 or 6 different strategies before you find one that actually gets you to the place that you're trying to go. That's okay. Don't feel bad about that. Give yourself plenty of room to work. Don't expect yourself to just walk right through these. This is something where you need to say, I don't know, let's go ahead and give it a shot. Let's see what happens if I do this. You need to kind of say it in this like sort of like positive light of just make an effort right here and keep going until you have no idea what else you do, and then say, that didn't seem to work out. Let's start back over and see what would happen if I instead did this thing right here. You have to kind of broad strategize across plan A, plan B, plan C, plan D, even maybe. Don't just get stuck right away. Don't just give up. But also, as with all good things, don't bang your head against the wall for 5 hours and never get anywhere. There's always an appropriate level of effort that you need to be putting in before you ask me questions, and you should be looking for that sweet spot right here of, I know that I've tried 3 different strategies and none of them work. Now I should go and ask Tony some stuff right there. Go down your checklist. Did you try sines and cosines? Did you look to see if there's any previously known identities that you can use? Did you try a conjugate? Did you add fractions together? Go on down, make yourself a checklist of all the things that you should think to try for any given problem, and try all those things before you ever even consider giving up or asking for help or something like that, right? So be persistent. This is not something that anybody should be expected to just be able to just do. This is a trial and error type of situation right here, and it helps you to go into it that way. If you go in with any other attitude, then you're just going to be really disappointed with this, and that shouldn't be what this is. Think of this as like a puzzle, which it really is. You're given the beginning, you're given the end. Your goal is just to get between the two by knowing both of these pieces of information. So good luck on your first journey with identities out there, and know that our next 3 sections are just building more and more and more identities that we can use to make these sorts of manipulations to our expressions out there, all with the goal that we're going to be able to solve some pretty complicated trigonometric equations by 7-7 and 7-8. So I will see you guys next week for section 7.4 when we introduce our sum and difference formulas. We're going to see things like sine, cosine, and tangent of alpha plus beta, 2 different angles, and we're going to come up with expressions that are going to be exactly equal to those expressions right there rather than having to go to calculators and stuff like that. So I will see you guys for that one next week. See you at 7.4. Have a good one, everybody.